In this episode, we will turn on the car's engine so it can move freely across the screen and decelerate gradually and smoothly when lifting the hand off the throttle pedal. No Name is here with you, along with my partner Coda. As always, we are here to simplify things. We left off in the previous episode after adding the car and the steering wheel, both of which are images. So, let's return to the race activity. To start coding right after the steering wheel setup. The throttle pedal we want to add is also an image, so we will use the image composable and fetch it from the project resources.
You can find all the images for this series via the link in the video description. Just make sure to save them in the following directory of your project.
And if you want exclusive car designs, visit our Patreon through the link in the description. After that, we need to add a description. Let's just use throttle. Next, let's start adding modifiers. First, we need the throttle pedal to be positioned at the bottom left. To prevent it from clinging to the screen edges, we will add some start and bottom padding. Let's set the image size to 75 dp. Let's test the code now. And there it is, the pedal has appeared. Excellent.
To make the throttle pedal clickable and provide a better user experience, we will use the pointerInput modifier. What's new this time is using awaitPointerEventScope, a function that opens a dedicated scope to wait for touch events as they happen. As long as the touch occurs, we look for two events. The first is the initial press. When this happens, we define a Boolean variable called as throttle clicked. Naturally, it will be wrapped in remember with an initial value of false because the pedal is untouched at first. However, once clicked, the variable becomes true. This brings us to the second event. When the user lifts their finger off the pedal, the variable resets to false. All of this happens inside a loop that repeats with every press. The primary benefit of this variable is that we can change the pedal image based on the press state, switching between the regular state image and the press state image. Additionally, we will scale down the pedal size when pressed, and return it to its normal size otherwise. Let's look at the execution. Now it really feels like you are pressing it.
To make the car move smoothly, we need to introduce a few variables and demonstrate how they function before moving the car. Everything will make sense once you see the mechanism operating before you. First, we need a variable to store the car's current speed, which will initially be set to 0. Then, we will define a variable for acceleration, determining how much the car speeds up when pressing the throttle. Let's set its value to 1. Now, let's use LaunchedEffect. Do you remember this function that allows us to execute its inner code only once? Let's utilize this single execution to inject a continuous loop. Its objective is to check whether the user is pressing the throttle pedal or not. If pressed, we increase the car's current speed. Finally, we will add a brief delay of 16 milliseconds between each loop iteration. Let's observe what happens with these new variables. Here is the car speed, and here is the acceleration rate. Well, when pressing the pedal, as you might have guessed, the car's current speed increases. When you stop pressing, the speed stabilizes at that value until you press again. This is both good and bad because if you keep pressing continuously, the car's speed will reach huge numbers and dangerous velocities. Therefore, we must establish a maximum speed limit.
Don't be surprised that the maximum speed value is set to 18. This does not mean 18 kilometers per hour in the real world. Rather, it represents programmatic units suited for the screen dimensions. Let's apply this threshold within our throttle check, ensuring that the current speed is always less than the maximum speed. Now, during execution, the speed will not exceed 18. However, another issue now becomes obvious. When releasing the pedal, the speed should start decreasing due to friction. Therefore, let's add a constant representing friction and assign it a value of 0.5. We will apply it inside the while loop when there is no pressure on the throttle pedal by subtracting this friction constant from the current speed, but only when the current speed is greater than 0. To prevent the speed from dropping below 0, we will reset it. Re-0.
Now, you can see exactly when the variable representing the car's current speed increases and when it decreases. What remains is to use this speed to actually move the car. Let's review this together. Currently, the car's position is static and relies on two fixed values. The first is half of the screen width, and the second is half of the screen height. However, to make the car move, we must define a variable. Let's create it and name it car position. To ensure the car's location updates dynamically, we will declare it using remember and mutable state of. Its type represents a point with x and y coordinates, and we can give it an initial value for now. To render the car at this initial point, we must replace the constant values with the car position variable, where x represents the horizontal axis and y represents the vertical axis. If we run the code now, the car simply appears at the new static location. As you know, to move the car, we must continuously modify the x and y values. However, this movement depends on the orientation or rotation angle of the car, whether it is moving upward, to the right, to the left, or downward. Each scenario requires altering x and y differently. The value we currently have to solve this issue is the car's rotation angle or direction. However, we need this value in radians, so we will use the math.toRadians function for the conversion. Fortunately, this is all we need to distribute the speed between the horizontal and vertical axes. In trigonometry, according to the laws of sine and cosine, multiplying the speed by the sin of the angle gives us the x component, which is the horizontal distance. Conversely, multiplying the speed by the cos of the angle gives us the y component, which is the vertical distance. Therefore, let's update the car's position variable by adding the new coordinates to it, the current speed multiplied by the sine of the angle for x, and the current speed multiplied by the negative cosine of the angle for y. That is all we need. Let's test the code. Perfect. Now we have a racing car moving smoothly in all directions. Great job.